Continuing our discussions on trigonometric equations. Let's say we have the following trigonometric expression. Cosine of 2x plus 3 sine of x minus 2 is equal to 0, and the domain restriction x is greater than or equal to 0, but strictly less than 2 pi. Alright, notice that there's no common factors to factor out here because sine of x and cosine of 2x are distinct. So there's really nothing we can do. Furthermore, there's no variable substitution like t is equal to sine or t is equal to cosine of 2x. None of that will be helpful in this situation. What we want to do is convert this cosine of 2x using a trigonometric identity, namely the double angle formulas, into a form that we could be able to solve for x. So hopefully a form that's quadratic in nature and either sine or cosine. We will note that in previous trigonometry sections, it can be shown that the cosine of 2x is equal to cosine squared x minus sine squared x. Okay, this is true, and it's matter of fact, it's a consequence of the fact that cosine of 2x is the same thing as cosine of x plus x. Okay. And that is the same thing as cosine of x minus sine of x for the double angle, for the angle addition formula for cosine. Then this reduces to what you have here, cosine squared x minus sine squared x. So just whenever you do cosine of alpha plus beta, set alpha equal to x, set beta equal to x, then that pops out and gives you this result. But whenever we utilize the Pythagorean identities, sine squared x plus cosine squared x is equal to 1, this, in the first case, when we solve for cosine squared x, allows us to have cosine squared x is equal to 1 minus sine squared x. And notice that plugging that in to this equation right here, for our cosine of 2x, if we replace cosine squared x with 1 minus sine squared x, we get cosine of 2x is equal to 1 minus sine squared x minus sine squared x. Notice that this breaks down to 1 minus 2 sine squared x. Okay? So this is another formulation for cosine of 2x. Furthermore, just like we solved for cosine squared x using the Pythagorean identity, we could have also solved for sine squared x. Matter of fact, that would equal 1 minus cosine squared x. And if we plug that into our double angle formula here, notice we would get cosine of 2x is equal to cosine squared x minus the quantity 1 minus cosine squared x. Distributing the negative, I get cosine squared x minus 1 plus cosine squared x. This reduces to 2 cosine squared x minus 1. So 2 cosine squared x minus 1 is also equivalent to cosine of 2x. So we have 1, 2, 3 different equations for cosine of 2x. And that is something we would be plugging in right here. Which one should we pick? Notice if we pick this one, we still have mixed trigonometric functions. Meaning, if we replace it with this one, we would have a cosine squared x and a sine squared x. Then it's not gonna break down anymore, because if this was a plus, it would be the Pythagorean identity. But unfortunately, it's a minus, so it's not the Pythagorean identity. Then, if we were to use this one, then we would have cosine mixed with sine, and then we wouldn't be able to utilize our quadratic techniques. It's much more appropriate to pick this formulation, because when we replace cosine of 2x with this, then we'll have an expression that's quadratic in sign, as you will see here in a second. Let me clear up some real estate here. So what we're going to do is pick the one in with the check mark, and so I'll delete everything else. Okay. Alright, so that means I'll replace cosine of 2x with this. So I get 1 minus 2 sine squared x plus 3 sine of x minus 2 is equal to 0. And then rearranging the terms, I get negative 2 sine squared x plus 3 sine of x. And then minus a 1 is equal to 0 because this 1 and that negative 2 meet up to give me a negative 1. Notice that now we are quadratic in sine of x, meaning if we do a variable substitution like t is equal to sine of x, that means t squared would equal sine squared x. And so this implies that our expression over here becomes negative 2t squared plus 3t minus 1, and that's set equal to 0. Alright? Here we have many techniques to solving this algebraic expression. It's a quadratic equation. We can use the quadratic formula, we can complete the square, or we can just factor it by brute force. Now, this is seemingly an easy one to factor by brute force because I can pick one of these to be 2t, and let's say a minus 1 times t, let's say a plus 1. Let's see if this works. This gives me 2t squared plus 2t minus 1. This, in fact, does not break down. So, and matter of fact, I just need to alter this here. I need to put a minus sign in front of this t. And so, let's see if this fixes it. Alright. When we put a minus sign in front of that t, we will get negative 2t squared, and that satisfies this piece. And then plus 2t, and then plus t, and then minus 1. So notice that this breaks down to negative 2t squared plus 3t minus 1. Cha-chink. That's exactly what we have right here. So this is the appropriate factorization of this equation above. So setting these two pieces equal to 0, that means I get 2t minus 1 is equal to 0, and negative t plus 1 is equal to 0. Okay? So I can delete everything we have here so far up to that point. And we cannot forget that t is really sine of x. So at the end of the day, whenever we solve for t here, we must then replace it with sine of x, because that's what t really is. We just switched it for a variable t so that it looks more familiar to us and that we're able to solve it using our algebraic techniques that we're trained in. So here, solving for this one, this implies that t is equal to 1. Here, solving for that one, this implies that 2t is equal to 1, and then that implies t is equal to 1/2. So this means that I have sine of x is equal to 1, and that implies that I have sine of x is also equal to 1/2. Okay? This gives us that, and this gives us that, because t was sine of x, as you can rewind and see. So over here, taking the sine inverse of both sides of the top equation, I get x is equal to the sine inverse of 1. Okay? And over here, taking the sine inverse of both sides, I get x is equal to the sine inverse of 1/2. Alright? Now, we must determine what is the sine inverse of 1 and what is the sine inverse of 1/2. So, you will note, and as you most likely know, sine inverse of 1 is a question that asks you at what angle does sine assume the value positive 1. And we all know that that is at the special angle pi over 2. So this is equal to pi over 2 plus all integer multiples of the period of sine. This period of sine is 2 pi. So all integer multiples of the period of sine are 2n pi. Okay? Now, x being equal to the sine inverse of 1, now we have to go to the unit circle. Alright? We notice that sine assumes the value 1/2 at pi over 6 and at pi minus pi over 6, which breaks down to 5 pi over 6. Okay? How do we know that? Well, because it's a special angle here where sine is 1/2. Furthermore, Over here, we go in the backwards direction to get that 5 pi over 6 is where sine of 1/2 is in the second quadrant. Because it's positive 1/2, sine assumes positive values in the first and second quadrant only. Okay? So we know that sine inverse of 1/2 is now equal to pi over 6 plus 2n pi, and it is equal to 5 pi over 6 plus 2n pi. Alright? So, what we have so far now states that we may write down all of the known information on the right hand side. We have x is equal to pi over 2 plus 2n pi. We have x is equal to pi over 6 plus 2n pi. And we have x is equal to 5 pi over 6 plus 2n pi. Now, what we must do is find explicit values, because these are the general values, and what we want to do is find explicit values, meaning we're going to plug in integer values in for n. And we're going to pick positive values to stay in our restricted domain. So when n equals 0, this goes to 0, this goes to 0, this goes to 0. So all we get for our answers is x is equal to pi over 2, pi over 6, and 5 pi over 6. Okay? When n equals 1, we notice that this becomes 2 pi, this becomes 2 pi, this becomes 2 pi. And 2 pi added to any of these values is a value that exceeds 2 pi. 2 pi plus any number greater than 0 exceeds 2 pi, and we could not exceed 2 pi to begin with. So none of the values for n equals 1 will work. So the only values that satisfy the equation and remain within the restricted domain are pi over 2, pi over 6, and 5 pi over 6. You can plug this back into the original equation and see that it is indeed a true statement, because when x is equal to pi over 2, for instance, this becomes cosine of 2 times pi over 2 plus 3 sine of pi over 2 minus 2. Okay? This reduces to cosine of pi. Cosine of pi is negative 1, so this becomes negative 1, plus 3 times 1, because sine of pi over 2 is 1, minus a 2. Okay, so this breaks down to negative 1 plus 3 minus a 2. Okay, and this is clearly 0. So, cha-chink, this is a valid solution to this trigonometric equation. You, at home, could go and plug in the rest of the values to see for yourselves that it actually satisfies the equation.